Yeah, thank you, Timo, for the introduction. Thank you to the organizers for the chance to giving this talk. Exact mixed integer programming, a status update on MIPS solving without numerical errors. So this is this is joint work with Leon Eifler, who contributed a lot to this work. You might have seen him yesterday in the poster session. And I think he's also in the audience. So I want to start this talk with a photo from the good old days. Chicago 2015 MIP workshop. I'm not in the picture of this pyramid, but I witnessed its construction, and I'm pretty sure in the audience we have a few smiling faces now, a few participants of this pyramid. Why Chicago 2015? Well, because this is actually the last time that I gave a presentation at MIP, and I had the chance to present something that's quite related to today's topic, an exact method for solving LPs over the rational numbers. And so to begin with, let me just give you a quick run through how this method works. And then later we come to mixed integer programming. So this LP iterative refinement is a hybrid precision algorithm, and it works as follows. We have a LP here in standard form, which we want to solve, and we first compute an approximate solution with a, say, double precision simplex solver or any other floating point solver to get an approximate solution xk and also a dual yk. And then what do we use this for? We compute kind of the residual errors, a b hat, which is the violation in the constraints, a shifted bound vector L bar, and the reduced cost vector C hat. And this we can use to set up a new linear program, P hat, which acts as a sort of a corrector problem. So these B hats and the product of L bar and C bar should all be very small if it's a good approximate solution, so say 10 to the minus 6 or something. And so what we actually do is we scale up this new data by a factor capital delta, which could be around 10 to the plus 6. And if we solve this problem, then actually the errors there become apparent again to a floating point solver. So we can get another approximate solution for this. And it turns out that this can be used as a correction for the original solution. So if you bring this back to the original space, scaling it down again and adding it to the xk and yk, then you get a new solution which is more accurate. And this you can actually iterate to gain arbitrarily high precision, of course, given that the floating point solvers function well and give reasonable answers. And so what this corresponds to visually or geometrically would be that we actually zoom in to the relevant area of the polytope that we're trying to optimize over and kind of get a higher and higher resolution to get a more and more precise primal dual solution. And at some point, you can also round this solution or have the optimal basis and can solve a rational LU system, a rational system of linear equations to get an exact zero violation solution. And so now I was presenting this at MIP 2015, but also Kati Volta was giving a talk on her work in exact mixed integer programming. And this is kind of the base that this talk now is built upon. This is also a hybrid precision algorithm and works as follows. So it's a branch and bound, and of course based on LPs, and so at each node we are having LP relaxation, which is, well, initially it's a fully exact representation of our rational input data, but then just solving this as an exact LP would of course be very slow. So the innovation in this approach was that we use floating point LP approximation. We solve this approximately, and then we tried some methods to correct the approximate dual bound that we obtain. So there is a hierarchy of dual bounding methods that can achieve this. Sometimes it may, of course, be necessary to really solve the LP relaxation exactly. For instance, if the floating point solver breaks down, or if the final gap is very small, and so it seems good to actually close this small gap by an exact LP solve. But often that's not the case, and then you can use cheaper methods. The cheapest method is called bound shift. Basically just directed rounding to correct the dual multipliers. And that's a method of choice if it works, but it relies on having finite bounds, at least where the reduced costs are non-zero. And so it cannot always be applied. So sometimes you need to use more expensive methods, and that was also newly developed in this line of research, a method called project and shift, where you use the approximate dual solution and you project it to the dual constraints and then shift it to get the sign constraints of the dual variables correct, or the dual slacks. And so this is more expensive, but it works much more often. And so this whole approach was much faster than just going the naive way of performing everything in rational arithmetic. It was a state-of-the-art branch and bound, not only in the safe dual bounding here that I explained, but also in the branching rules. So it applied strong branching and reliability pseudo-cost branching. And so it was definitely the state-of-the-art at that time. But we all know that branch and bound is not sufficient, right? The modern MIPS solvers use a bag of tricks of supplementary techniques to actually get the performance that we've seen and that can solve large-scale problems. And so basically there was an algorithmic gap between this hybrid precision branch and bound and the state-of-the-art MIPS solving, not in terms of exactness, but just of all these supplementary techniques. So there was no pre-solving, no domain propagation, no cutting planes, no conflict analysis, no primal heuristics. And also it did not use this new method, LP iterative refinement, to solve the exact LP relaxations. And well, there's actually a star. So I have to make a comment here. So this is true for this paper from 2013 by Cook, Koch, Steffi, and Volter. Kati Volter has experimented a bit with an early version of this LP iterative refinement, but the solver, this version of exact skip, was still relying on Q sub x for the exact solution, because that version of Soplex was not yet able to really go fully zero tolerance violation. And so, well, what do I want to present to you now in the remainder of the talk? We addressed basically 3 of these issues. So we extended the framework to add rational pre-solving. We extended it by primal heuristics, and we integrated the exact version of Soplex, which uses LP iterative refinement. And so, yeah, fast forward to now. So it's about 2 or 2.5 years ago that Leo and MIPLIB picked up this project and started to thoroughly revise this exact version of skip. So in several points, first of all, he looked again at the hybrid precision branch and bound and analyzed it, integrated it into a more flexible code base, and also improved some performance issues. Then we integrated Soplex as an exact LP solver. We added rational pre-solving, primal heuristics, and also we included certificate printing so that you can verify the result of this branch and bound independently of the solving process afterwards. And so this will be a very computational talk in the following slides, but I want to give you a peek preview of what we have achieved overall. that is approximately an order of magnitude speed up compared to the original framework, and about 3 more instances solved on MIPLIB 2017, 3 times more instances solved on MIPLIB 2017 benchmark. And so I want to present to you all these improvements along with the computational results, so not separately, but please at any time, also the moderators, feel free to interrupt me if there are any questions that appear in the Q&A session, in the Q&A. So that you know kind of what kind of numbers you will look at now, here's an overview of the experimental setup, how these experiments were run. So we use 3 test sets. Because we want to compare to the original framework, we wanted, of course, to use the same test sets that were used in this paper from 2013, and these are called FP-Easy and NumDiff. FP-Easy was selected to be easy to solve for the, at that time, current version of the floating point skip solver. And NumDiff was a manually curated test set of numerically difficult instances, which was judged by looking at condition numbers of LP relaxations and the like. But then we also wanted to have a more modern and larger test set. So we also included MIPLIB 2017 benchmark. We threw out all the instances that are hopeless and that would just time out in all experiments. We excluded ones that could be solved by floating point, could not be solved by floating point skip in 2 hours time limit. 2 hours time limit was used for all runs, 3 random seeds, except when comparing with the original framework, because that was not possible there yet. And well, in the results, we also include instances where both versions that we compare time out, because that just dilutes the results. So it's kind of a one solved subset. So at least one of the versions always could solve these instances. All right, so let's get started. What was the first step that we took? So I said a thorough revision of this basic hybrid precision branch and bound framework. Here's a selection of probably the most important changes. So we enabled the use of the objective limit in the floating point LP solver that was not present. And it's actually a bit less, it's a bit more non-trivial than it sounds, because these dual bounding methods, the safe dual bounding steps, they always weaken the dual bound of the floating point LP solver. So if the floating point LP solver stops, then the corrected safe dual bound might actually not violate the objective limit anymore. So we have to implement some relaxation strategy for the objective limit that we give to the LP solver. Then we save some computation time by checking primal solutions, not always exactly in rational arithmetic, but we use a cheaper version of interval arithmetic. So it's called running error analysis. When you compute the activities of a linear constraint, you can actually do this just in floating point arithmetic and compute the error that you might potentially make. That's sort of weaker than interval arithmetic, but it's even a bit faster, and you can use it to just rule out some solutions before actually having to do the rational check. Then we employ this project and shift method a bit more aggressively. That's a tuning step, and we also solve exact LPs a bit more often to decrease the tree size. That paid off. And in this table now you see many numbers of the results. On the left, the original framework, on the right, the new framework. We compare solved number of instances, running time, number of nodes, and the dual bounding time, the time that was spent in the safe dual bounding methods, either exact LP, project and shift, or bound shift. And if we look at the solved instances, then we actually see a slight improvement that we can solve more instances, especially on the MIPLIB as well. And this is also reflected in the running time. Except for the NumDiff test set, there we don't see that much. But on the others, basically, this very much comes from the number of nodes reduction that we have. So basically, this comes a bit from these smarter use of project and shift and exact LP solvers. But yeah, that's also to be expected. We have not added any revolutionary techniques here. And so in the second step, we exchanged the exact LP solver. Previously, we had QSOPT-X, which has a form of incremental precision boosting implemented. So basically, it solves floating point LPs at double precision, quad precision, and increasingly high levels of precision until the basis is optimal. And Soplex also solves floating point LPs, but always on double precision level, and can use this iterative refinement strategy to increase the accuracy. And so the results that we see here are that we can solve more instances weight, not everywhere. So we actually lose some instances on the NumDiff test set. We actually lose as many instances as we gained in the first step, 6. And this is actually quite interesting and also not so surprising. So QSOPT-X might be a bit slower, but actually it is numerically more robust because it can increase the precision of the floating point solver that it uses. While Soplex in its current implementation is completely reliant on the fact that the double precision floating points works. And so it's not surprising that on some numerically difficult instances, Soplex might have troubles. And this is exactly what we can see in this experiment. So that's why this is interesting. And that also shows that actually a combination of these two LPs, exact LP solvers, might be very beneficial. So an iterative refinement strategy, but that can also boost the precision of the floating point solve when it's necessary. So this is an interesting outcome of this experiment. And if you look at the time, however, then it's very, very clear that exact Soplex is a good idea. So you become much faster, so 60% faster on the FP-Easy and MIPLIB test sets, and also for about 40% faster on the numerically difficult instances. And yes, this is not coming from smaller tree sizes, but just basically because we reduce the time needed for dual bounding. Okay, second step. We have now a new exact LP solver, but then next we go to really add a new algorithmic technique. Oh no, here I forgot, we actually have some more detailed analysis on this exact LP solving. So let's take some time. So what I said is the time is reduced drastically, and this can also be seen here where we measured the time per call to the exact LP solver. And you see that the numbers in the time per call columns drop drastically. So 76, 60, 65%. So this is really where the speed up comes from. And then also it occupies less percentage of solving time. Okay, so but now for the first real new algorithmic technique, and that is symbolic presolving. So how did we, the interesting question, I guess, is also how did we implement it here? Because so basically this is not a hybrid precision component. We simply use known pre-solving techniques that you know from the MIP literature and execute them in rational arithmetic. And how is that possible? So this is from a different project called Papillo, which is a new software library that I've developed with Leona Gottwald and Alexander Höhn, and that stands for Parallel Pre-Solving for Integer and Linear Optimization. And this is a matrix-based pre-solving library for MIP and LP. And the special thing why we can use it here is that its arithmetic type is templatized. So you can use double precision or any other level of extended precision, but also rational arithmetic through GMP. And so this made it convenient to integrate this into the new exact script. What is another nice feature of this software library is that it tries to use the parallel hardware resources that we have on modern CPUs. And this can help to mitigate a bit the computation overhead that we have from using rational arithmetic. not fully, but on some instances, on some outliers, this really helps. And the results you see in the table above. So let's first look again at the number of solved instances. There we get a consistent boost in number of solved instances. And particularly also we see it in the NumDiff test set, where we go plus 18 from 54. So this really shows that the presolving is not only about reducing size and tightening the LP relaxation, improving the formulation, but also about improving the numerical properties of a mixed integer model. And this is also reflected again in the massive time reductions that we have here. So especially on the NumDiff test set, where we are 84% faster by enabling pre-solving. And this is also pre-solving on average takes virtually no time, so less than a second. Yeah, and so this is quite a nice result. Yeah, improves the usefulness and the power of the exact LP solver for solving to optimality. But it's not only about solving to optimality, of course. When you want to use such a solver in practice, then also primal solutions are important. And so we have integrated here now the heuristics that are available in default skip. This again follows the hybrid precision paradigm that we have seen in several algorithms now. That means try to use as much cheap floating point arithmetic as you can, and as little, but as much as necessary, of course, exact rational arithmetic, because that's expensive. And so how do we do that? We did not implement now new primal heuristics that use rational arithmetic themselves, because that might be slow, but we just execute the floating point heuristics that are available in skip. So the diving heuristics are run on the floating point LP relaxation. The submip heuristics solve submips as floating point MIPS. Cheaper rounding heuristics, of course, just can use floating point arithmetic as well. And all of these produce solution candidates. Of course, they will very, very rarely be feasible. And so what we need to do afterwards, we have a repair step where we just round the integers, fix them, and call an exact LP solver to compute exact values for the continuous variables. And this, yeah, you could just execute as such, but this might actually produce, especially in the beginning of the solving process, quite a couple of solutions, and especially at the beginning also maybe some not even so great incumbents. And so we've additionally implemented a buffering scheme. So when such a heuristic FP, a floating point solution comes in, then we first check, is it much better than the incumbent? Does it significantly improve the bound, or does it have the potential to significantly improve the primal bound? And if that is the case, then we process it immediately. Otherwise, we add it to a buffer and we check whether the buffer is full. Skip if it's not yet reached the threshold. Otherwise, we start with the most promising candidate in this buffer. And so we might save some work. If this is already feasible, then we can discard lower quality solutions. So we fix integers, and then also we don't immediately solve the exact LP, but obviously it can happen that different heuristics at different times produce the same integer fixings, the same solution candidates. So we want to avoid processing them twice. So we have a hashing mechanism to check whether this fixing was already processed. If yes, we throw away the solution. Otherwise, we solve the exact LP and hope that this improves our primal bound. What's the impact of this? So here you see without heuristics on the left and with heuristics enabled on the right. Solving time impact is not so great, but that's also not so surprising. We know also from floating point literature that primal heuristics don't affect time to optimality that drastically. But where we have significant improvements are time to first solution and the primal integral, which is affected, of course, by the time to the first solution. And so this makes the solver much more usable, I would say, in practice, also for instances where you cannot solve to full optimality within your time limits. All right, so this rounds up the extensions that we have. What's now the overall impact? And this we measured on the MIPLIB benchmark set. We compare the original framework now with all components that I just described in the new framework. And there, the first thing that we can observe is that we can solve significantly more instances now, instead of 1853. But of course, that also shows that the state of the art between floating point solvers and these exact solvers is still quite large. But we've made a significant step in solving to optimality. And not only that, also on the instances where we cannot solve them, that we cannot solve to optimality, we now find significantly more feasible solutions. So about a factor of 2 more feasible solutions found, and a factor of 3 more instances solved. But I guess the most satisfying result is the reduction of running time between the original framework and the new framework. And this is about 90%, so about an order of magnitude speed up when you exclude the instances, of course, that time out with both solvers, they just dilute the result. This is also reflected here in the performance profile that you see at the bottom. And so now to wrap up, well, we've seen that this round of error-free MIP solvers, or MIP solving, is still far from competitive with what we have in the floating point world. But I think we've also seen that there are no fundamental roadblocks to exactifying all these techniques that make floating point MIP solvers so fast. So we've demonstrated this in this work for pre-solving and for primal heuristics. But of course, there's a way to go. Cutting planes is the natural next step. The code is available, a new version of this exact skip and a version of the Papillo pre-solving library that allows rational pre-solving on GitHub, but also in future releases. And for more details in these results, there's also a preprint available on Optimization Online and a paper that was just presented at IPCO last week. So thank you very much for your attention, and I'm very happy for any questions that you might have.
Okay. Yes, thanks a lot, Ambros, for this very insightful talk. Exactly half an hour. That's great. And I hope we get some precise questions now for you. So Pierre was asking, can you give us an example of problems for which obtaining exact solutions is critical?
Yeah, that's a very good question. So, I mean, I think there are 2 classes of problems. So one is just very general MIPS, which are numerically difficult and where floating point solvers give strange results, might give inconsistent results, and you're not sure what the exact optimal solution is. Because you can also use these exact solvers, I mean, not only to solve to 0 tolerance, but to solve exactly to numerical tolerance as we have it in floating point solvers. But then there are some real applications, like if you want to maybe use this in mathematical, in experimental mathematics, if you want to have if you have a conjecture in combinatorics that you can formulate as an IP, then you really want to be sure that you have not found, for instance, a counterexample, right? That the problem is really infeasible, and then you can use this for proving some mathematical type of theorems. Or in verification problems like chip design, if you can model the question of correctness of a chip as an integer program, then you really want to be sure that the MIP solver gives you the correct result.
Okay, cool. Maybe one more question. How about conflict analysis? Something that I find personally interesting. So is the techniques that you use, is this just a that you would need for this? Is this just a combination of exact LP solving, also iterative refinement, and exact pre-solving / dominant propagation? Or do you think you will need any more?
Yeah, that's a good question. I mean, this is like two questions. So one is the question, how do I create conflicts? Second is, how do I propagate them? So I think for propagating them, that's just propagation of linear constraints essentially in MIP. And so there you can use directed rounding to do that safely, or even this running error analysis that I've quickly mentioned. For how to create conflicts, I mean, that's basically you have to analyze the dual proof of the LP. That's one way to do it. I think there you can use something similar than what is used for the safe dual bounding. So for how to create a safe dual bound, you can also use or adapt these techniques to create a safe Farkas proof for infeasibility, and then from there on start like create your conflict.